So let me talk about why Hello World is a massive operation. I know printing Hello World seems rather, mundane, but under the hood, there's a massive operation going on. And here I am to talk about it. So, yeah, before I go on, let me tell you who I am. Hi, I'm Richard Rowland. I come from Tokyo, Japan, and the flight was 20 hours long, so I'm jet lagged, but I'm very excited. The adrenaline is important. I work at OKCoin Japan, a global cryptocurrency exchange. Just a personal word on cryptocurrency exchanges. I know there's been some news about it recently, but thing is, we're located in Japan, and the regulations are different. So we're not allowed to do anything with customer funds. So this is how I hope to stay employed at this company. My hobby. These are the photos I took. The first, that's at the US Air Base. The other three is in Kyoto, Japan. So this is why I have my stage prop to convince you all that I'm a photographer. This is going well. Projects. Back in college, I created a method to semi-permanently store data. So you know how data disappears when a server crashes or becomes unavailable? In order to mitigate that, I decided to store the data on the blockchain. And we also use a P2P system called Interplanetary File System, IPFS. That's on GitHub. If you want me to talk about it at some conference, please let me know. I'm happy to talk about it. So let's talk about how Python programs are executed. And once we know about this, maybe we could become a better debuggers next time we write a Python program. So Python, whenever we compute our Python programs, we have Python code converted into intermediate representation. And that intermediate representation is turned into bytecode. And bytecode is then executed inside what we call a virtual machine. So just an icebreaker, what kind of language is Python? Let's raise hands. If you think it's A, compiled, raise your hands, please. Great. If you think it's B, raise your hands, please. Thank you, thank you. Well, the answer is both. It's surprising, but Python actually compiles and interprets. Let me talk to you about what these terms mean. So these different models of program execution. So when you say compiled, you guys might think of C, C++. Basically, you have a source code, and you just turn that into CPU instructions. Now, if we say interpreted, we procrastinate, and we start executing only when we're starting it. And then we start generating the CPU instructions. So a famous programming language would be, say, JavaScript. Now, what we have is a best of both worlds. We generate, which is intermediate language, we generate the bytecode, and we convert that into CPU instructions in the virtual machine. So basically what this means is we kind of have something that is like a CPU instruction, but we load that into the virtual machine of the respective computers. This way, like Java, we could have write once and run everywhere because the virtual machine has the optimizations for the differences of each system or a machine, say a Mac, Linux, or Windows. You don't have to worry, you can worry about less if you write that with an intermediate language. As a matter of fact, Python has several execution environments. There's CPython, the famous version that we all know and use probably, written by Guido van Rossum. There's also PyPy, which is Python written in Python. That's very meta. Nerds have a very macabre sense of humor. And there's also JPython, Java. It's basically running in the Java virtual machine. And there's also IronPython, which runs in .NET. Now, I would speculate that we have all these kind of execution environments in different languages because especially in the enterprise world, they're less flexible on the programming languages they choose to run in. So that's why they have their own implementations in the language of their choosing. But today for this presentation, we're just going to talk about CPython, just so that we're all familiar with it. So, what is Python? The best way that I would characterize it would be in two parts. We would have the programming language specification, so the syntax and what have you. And we have a Python execution environment, where it takes that syntax and converts that into machine code. What that means is that the program that we write, that's the programmer's concern. That's what we should worry about. But the execution environment, we don't have to worry about that. That's Python's concern. So CPython, in order to run these, the source code that we write, has these features. The lexer tokenizer, parser, the compiler, the virtual machine. How these things work in tandem is like this. So let me walk you through. First, you have the source code, the .py that we're familiar with. Once we say, run this Python, we have this thing called tokenizer that works first. And that converts that into what's called a concrete syntax tree. We'll go over what all these are later. The CST is taken by the parser and then put into a more meaningful semantics called the abstract syntax tree. And the compiler takes that and then turns that into bytecode. And finally, when the bytecode is taken, we could just give that to the virtual machine, and that is run on a CPU. So first, let's talk about the first step, the Python code to CST. So we have a set of rules for Python, like what kind of symbols we can use, what we can't, how variables are declared, and what have you. These are called grammars, and they're stored in this project directory, CPython grammar tokens. And once the tokenizer scans through each character, it divides them into each of these tokens, or a unit of these characters. So let's say let's try to look at a tokenizer. Here we have a simple hello world. If we say tokenize, it starts from the top. It says, oh, this is UTF-8. We have print. We have a bracket, hello world, another bracket, and we close it. And then once we have all the tokens, we kind of make that into a graph or a tree. Now, in text representation, this is what a CST looks like. It's actually pretty complicated because it has all the semantic information, whether it be a trailing white space or all the information about the text of the Python program. If we visualize it, it kind of looks like this. It starts to look like a graph. Basically, the CST takes the expressions and tries to put them into some order. Now, I had to abbreviate it because the previous textual representation you saw was pretty long. So now we give more meaning to the text. We create what's called abstract syntax tree. And the abstract syntax tree is created with what's called a parser. Now, Python used to have a parser called LL, which was written by Guido himself. But since Python 3.9, we had a new kind of parser called the PEG, Parser Expression Grammar. This basically has more efficiency, and it takes advantage of the recursive functions. You could read all about this in the Python enhancement proposal. As a matter of fact, all these language features are actually defined in the PEP, so you could always read them. It's just a little technical. So once we try to generate the AST with hello world, this is the kind of thing that we get. It's much more simple now. It's more legible. And we could kind of see that Python is understanding that, oh, there's a print function. There's a constant called hello world. We haven't given it any arguments or keywords. And we got a call on that function. We're starting to get into the program's brain. As a matter of fact, ASTs are usually represented in trees. This is generated by InstaViz, a Python module. It's very famous for debugging, and it's used in some Python internals documentations. So this is the tree that you have, and basically you could kind of see the dichotomy, what kind of things belong in what kind of groups. Now, compilers are a very complicated but fascinating subject, and maybe some of you may have heard of the Dragon book. This is what it looks like, the compiler's book. I actually skimmed some of it to prepare for this presentation. But yeah, it's dense, but this is how Guido got his understanding of to create the Python program language. If you want something simpler, we have a book called Crafting Interpreters, and this is a book where you make a pseudo language, your own programming language in Java. And this is a simpler but very intuitive way to understand how compilers work, because you make them step by step. Now, let's talk about compiling them into bytecode. So if you want to see the compiled representation, you run the module pycompile. So the Hello World program that we used above is now represented in hexadecimal, just like this. What does this all mean? Well, here's some information. So in the header space, we have the first 4 bytes. That's called the magic number. And basically, it shows that, oh, this bytecode was generated with this version of Python. So whenever a virtual machine sees the bytecode, it's going to say, oh, is it compatible with my version of the virtual machine? If it isn't, it just recompiles. If it is, it takes the cache. The next 4 bytes is the padding with a series of zeros, and the rest is serialized Python code. The header format is actually interesting because there's been a debate about how to change that in PEP 552. And basically, they've added another word. Word is basically a length of bytes. So they had a 32-bit word added, just to make it so that it used to be a timestamp based. Basically, whenever you compile, it takes the time from the computer and say, oh, this is a new version because it's compiled at this time. Whereas now, they use a checksum version, which basically means, oh, the content of the program computes into this magic string, a text of string. So if we compare that, we could see, oh, it's been changed or it's not been changed. So where is the bytecode generated? Well, this bytecode generation is implemented in the Marshall module. And in the CPython project, we could see it in the include marshall.h and the Python marshall.c. So let's look at how Hello World is compiled. This is the Hello World that we have. If we compile it into bytecode, this is how it's stored in the memory, how it's represented for the computer. Basically, it turns into a thing called a code object. And in a hex representation, it's a little difficult for us humans to read it, but that's what the computer sees. It also has these information surrounding an execution, like constants. So we have none in Hello World. We have none because the program is going to return none at the end of the execution. I mean, it has to return something to say nothing has happened, therefore it's okay. And we have Hello World. We also have names. So that's the name of the functions, the variables, of what have you. Yeah. So let's decode the first byte. So the first byte, we have t. So what is t supposed to be? Well, if we represent that in a numerical format, we could do that by using the built-in function ord, short for ordinal. and it becomes 116. Well, what is 116 supposed to be? Well, we have this module called dis, and basically that takes it's a list of operation names, which has a table of operations. So operation number 116, if we will look it up, is called load global. So from this, we know that the first operation it does is load global. As I said, this is a module that's used for decoding the opcode, and it's included in CPython. So what is the opcode? Well, if you want to see all the opcodes, it's included in the include opcode.h file, and it converts all the opcodes into numbers for the Python execution environment. It's listed from number 0 to 255. And if you want to read all of them, it's listed in the dis documentation. So let's look at the instructions inside the Hello World bytecode. Well, if we use dis and we disassemble the hello function, this is what we get. With annotation, it means this. So first, we load the print function. Then we read the variable content, hello world, and we call it. So what that means is first, before you let the machine run, you have to load these things into the memory. And then once you call it, you can execute it. And the result of the execution, you could get that by doing pop top. And then in order to return none to end the program safely, we called a constant none, and then we return that value. What does this all mean? What is this thing called stacking up and all of that? Well, Python works as a, what's inside a virtual machine? It works as a stack. And stacks are useful because they're a simpler representation of the execution. It executes in compiled intermediate language. And because it's stack-based, it's easier to support many platforms, Mac, Windows, Linux, what have you. Let's talk about stacks. So what is stack? It's like the Tower of Hanoi. Basically, you execute the data from the top. And in comparison, it's different from a register-based model like LLVM, which writes into the array inside the memory. But the details about that is out of the scope of this presentation. How is the VM implemented? Well, it's a very long file. If you look at the Game Boy presentation that we had a couple sessions ago, it's rather similar. But for each opcode, you have to implement instructions. And all of that is implemented in a very long switch statement in C eval.c. Basically, we start with no operation, which just dispatches to the next line of function, stuff like that. Now, when we execute a function, there's an important concept that we have to know called the execution frame. Basically, this indicates the program scope. We have 3 kinds of stack in the execution frame. The call stack, which is mostly concerned with the function. The evaluation and data stack, which is concerned with the state and the content of the variables. And we have the block stack, which handles all the control flow, like if you have like a if-else statement. So in order to better understand how these execution frame works, let's have a recursive function. Here we have factorial.py. I'm sure some of you are familiar with leak coding and stuff like that, but this is how you could just recursive call the function itself until you reach a end condition and start calling back. If we visualize that, it's going to look like this. So if we have a factorial of 3, then first we establish the main frame. And the main frame will will call the frame called factorial. And inside that, we have factorial 3, factorial 3, and minus 1. And that, and if we go to the rightmost functions, or the stack, that's the top. So we first handled those things. And because it's 3 minus 1, that turns into 2. And now we have a function of factorial of 2. Well, how do we execute this? Let's call another factorial frame. And here in this frame, we have a factorial of 2 times factorial of 1. And the variable here is n equals 2. How do we execute factorial of 1? Well, we call another factorial frame. Here, factorial is 1. In this condition, we told the program that if you have factorial of 1, then you return 1. So let's return the result through the previous frame. This becomes 1, so it's now 2 times 1. So the result of this frame, we now know, is 2. So that we return that result to the previous frame. And now we have 3 times 2. Well, now that we have 3 times 2, we know the result. So return that result to the previous, or the main frame, and we get 6. Whew. So what did we go over? We went over the Python execution flow, basically how Python code turns into the intermediate representation, and how the intermediate representation turns into bytecode, and how that bytecode is taken by the VM and is executed in each user's machines. Now, if you want to learn more, these are some good resources. So the Python Developer's Guide is a more brief document, but it's a very good starting point because it tells you how all of these CST and AST generations happen, how bytecode is generated. It's a good point. If you want to get some help from these experts, you could use the Python mailing list. Some good lists for this topic are Core Mentorship and Python Dev. As a matter of fact, in order to prepare for this presentation, I did send a question to a Core Mentorship. They were very kind. It was kinder than Stack Overflow. I wish the word was more like this. And they gave me a lot of resources. They guided me to the appropriate PEP, and that's how you could get a lot of help. These people are core developers. They know what's happening inside. And it's amazing that these people can give you time to answer your questions. So there's no thing as being scared of because I'm a noob. As a matter of fact, if you just subscribe to these mailing lists, it's really fun because you get a lot of interesting questions. Sometimes you have emails from NASA. Other times you get emails from Guido van Rossum. It made me feel like a celebrity. Now, if you also want to read some books, some good ones are Inside the Python Virtual Machine, because it talks about how bytecode is taken by the virtual machine and is converted into machine instructions. What I like a lot, and a lot of Python speakers have always referenced this, is called CPython Internals by Anthony Shaw. This book is published by one of the most famous Python tutorial sites called Real Python. And basically, this book takes you from all the, it goes into more detail than I did in this presentation, talking about how Python source code is transformed into trees, and trees turn into the bytecode. It even talks about how the compiler sets up these functions, and it's a very good overview on how the internals work. So I would definitely recommend that. And with that, I exit from my presentation. Thank you for listening.
Thanks, Richard. Any questions?
Hi, thank you. I'm curious to know if, in your experience, you ever had to go down this level of details to solve a problem, like looking at the syntax tree or something like this?
Oh yeah, so I meant to say this in the presentation, but you don't really have to go through these detail because that's what abstractions are for. The Python developers don't want you to worry about what's happening inside. The problem is that when I was making my my blockchain program in Python, and that's when I got my interest in Python, I was wondering why I keep getting these error messages, and I got really annoyed. So after I submitted my thesis, I began to explore into the Python internals, and it turns out it's pretty useful to have to understand what's happening inside Python, so that whenever you get like an error message, you could better interpret it. So it does make you a better programmer.
Actually, could you get into that a bit more? What do you mean by, by knowing the CPython internals, you'll understand error messages more? What does that mean?
So let's say like if you get an error message, the first thing you get is the call stack. When I just jumped onto Python just to get my thesis done, I was scared by that word. What's all these functions happening? I never programmed these, and yet these terms are appearing. So once you start running these programs, sometimes most of the time it's the programmer's fault for having these bugs. But in order to recognize how these bugs happen, it's better to see how all the code is handled internally. And if you step and trace it, then you become what's that noise? You understand that better.
Hi, I have one question. When you specifically run Python -mcompile and hello.py, then you are converting it into bytecode. But let's say we talk about a generic web application, let's say Python Django or Python Flask web application, where a lot of files are just importing and you just run the final file. In that case, bytecodes are not being generated for all the files, right?
I'm sorry, I'm struggling to understand your question.
Okay, so I'm talking about a generic application, not a standalone single file. So when you run an entire application made in Python, so that doesn't get converted into bytecode.
Oh, so if you write a program in Python, I hope I am addressing your question. If you write a program in Python, that is then taken into the compiler, and you get the compiled version, which is bytecode. If you compile it in your project directory, you're going to see a directory called _pycache. And basically, that stores all of the compiled Python code. So the extension of those files are called .pyc. That's Python compiled. And it does store the compiled version of the program that you wrote.
But still, you need original code in your virtual environment, right? In the source code. Like, source code is still accessible in your virtual environment directory. Can you make the application work entirely based on bytecode and I remove the original code? Will it work?
If you remove the source code, after you compile,
yeah.
Okay, yeah, it should, because it is. The bytecode is the source code anyways. It's just in different representation, and it's less human readable, but it is still a program. As a matter of fact, if you're into a binary analysis, basically what you're doing is you're reading the compiled version of the program, but just because it's a machine instruction doesn't mean you can't understand it. If you use like Jira or GS, all those reverse engineering, reverse compilers, that's what you see. It is the source code. It's just not readable, so you could always just trace back and see what's happening.
First, thanks for your talk.
Thank you.
This is lower level than what I'm used to, but I'm curious because also I think the hot new thing is that 3.11 is faster, right? And I think it has to do with like garbage collection and whatnot. So I was wondering if you could put that in context, like where are the changes? Is it in the bytecode to like, or is it before, or do you have no idea? Like how can we make how could they make Python faster? And also put in context with like the JIT compilers like Pigeon and PyPy and everything. What are the differences? Do you know?
Ooh, the thing is, I haven't dug into the internals of 3.11. I just started reading into that, but it is interesting that they made it faster. So.
And do you have any guesses as where are the changes? Like, because for developers, the syntax it should be the same, right? So I imagine it's from bytecode to machine, or?
Yeah, it's somewhere in the compiling process, and I personally haven't identified it, but that could be a subject for future talks.
All right, thank you.
Thanks.
So I just wanted to add a point. Your man was asking about if you left over PyC files in a file or in a directory, would they be able to run if you took away the backend source code file? I'd say anyone in here that's done extensive unit testing has at some point moved a unit test file into a different directory and then accidentally ran the old one. So the answer is yes, and it can be really troublesome because you end up using cache version of the Python file despite your changes, and you're wondering why your code isn't being represented. Your code changes aren't being represented.
Okay.
Just a point.
Thank you, thank you. I guess it must be in the implementation of the unit test libraries, but okay, thank you.
Any more questions?
Yeah. So we talked about CPython source code, disassembler, and opcode. There's other, like implementation like PyPy use the same opcode and they have slightly different.
Oh, I'm not sure about the PyPy internals. Yeah, I haven't looked into that.
My question is, I don't know if you can go a little bit deeper, because I know we are a little on time, but if you can go deeper in terms of the garbage collector and the memory efficiency in the internals of Python, because we only see here like the execution, but many times we don't know about the internals, about how the memory is used, how it's optimized in terms of running, execution, and all the stuff. I don't know if you can go a little bit deeper about that, if it's the garbage collector used in the virtual machine.
Well, yeah, that is a pretty big subject, actually, so that's why I removed it from the scope of the presentation.
Oh, okay.
We have time for one more question.
Have you ever had cause to implement any C code and subsequently kind of expose it in Python? And what's your experience with that?
Can you please state your question again?
So implementing your function, your code in C and exposing it then to your Python program for performance reasons, or is it something you've ever had to do or had experience with?
I don't develop. I haven't contributed to the CPython project yet, but basically there's a code portion that's written in C and there's a portion written in Python. It runs in C in order to compile and do the low-level stuff, but all the abstractions like the data structures and the primitives, even strings and like integers and stuff like that, that's stored as a data structure called PyObject, and that's implemented in Python. So yeah, it does use both Python and C. I think it's possible to write some C code and expose that to your Python program and call it upon.
Okay, thank you.
Thank you. Thank you so much.
Thank you.